Okay, so let's make a start and other people can join if they come. So like I said, in this session, I'm going to talk about economic appraisal of the energy projects which are used for investment decisions. So they are, apart from one bit, they are not necessarily for energy projects, they are for any investment projects. But now we'll relate it more to fever technology and energy. So what I'm going to do is to give you a quick introduction of why we are doing this at all, and then I will talk about some popular methodologies that are used for investment decisions, and that is cost-benefit analysis, which is based on discounting and net present value, internal rate of return, real option, and LCOE, which some of you are familiar with, it, levelized cost of energy. Generally, when we have something like a fever technology that needs a private investor to invest in it, they want to know whether they should go ahead with this project or not. So that is one reason we are doing this investment analysis. And the second thing is maybe you already have two different projects. So for instance, in case of fever, it can be a project that it is completely based on solar energy. And also it can be another option too, that you are basing it completely on wind energy, and then you want to decide between this solar and wind projects, which one is better for you to go ahead. Now, there are many methods that you can use, but they can be categorized into two categories. The first set are the ones that they are not using any discounting, such as the simple payback that I think Yuan had used in his calculations and presented to us. And the second set are the methodologies that they actually use the idea of discounting. And those are the ones that in the economic appraisal, they are mainly used. And I'm going to talk about them here. In terms of the idea of present value or the future value, depending on what you want to use, basically the value of the money that you have in future, for instance, in year T, is not the same as the value of this money in the present value in the base year, year 0. So for instance, if you are talking about 100K, the 100K in year 2030 doesn't allow you to buy or do the same investment as now in the base year 0, which is 2023. So in a way, you need to discount that future value in 2030 to the present value in 2023. For that, we use a discount factor, which basically this discount factor uses a discount rate in the market for the investment, which is I here. And then divides the future values, V stands for the future value, by 1 plus I power T in close brackets. And T is the number of the years that you are trying to discount into the present value. Normally, you use this up to the lifetime of the project. Now, in the cost-benefit analysis, you are trying to maximize the benefit minus cost or the net benefit of the project after it has been discounted. So that's what you are trying to do. So whichever has a higher net benefit for you, that is what you would like to have in your investment. Now, in some of the methods, as you will see, is the other way around. So it is easier if you actually change the present values to the future values. So V is a future value, as you see, if you just take the formula above for the present value other way around, rather than multiplying it by 1 plus I power T into your present value, we'll get the future value. So for instance, the value of money in year 1, which is 2024, you want to just convert it to year 2030 if that is your final year in the project. And you will see we will use this method, but the majority of them use the present value one. In the net present value approach, firstly, I have to mention it's only for the private appraisal, because we have a private appraisal as opposed to the social appraisal. In terms of fever technology, we are looking into the private investment, and all of these methodologies are based for the private appraisal. So in the net present value, what you do is that you need to have the present value of all of the cost or expenditure. So E stands for the expenditure, PVE is the present value of the expenditure, 0 is the base year, which is 2023. And normally in the base year, you have the capital cost of the project. So you are building the fever technology, putting the solar panels and wind turbines and your batteries and everything. And then from assuming that the time to build this project is only 1 year, you might not have any revenue in the first year, but in the second year, also you have some expenditures, which in terms of renewables, it is generally smaller, as you know, as opposed to fossil fuels, because the operation and maintenance cost is smaller. But for instance, if you have to replace the batteries over time, I mean, you engineers, you know better. So maybe if the lifetime of the battery, I don't know, is 2 or 3 years, and after that it has to be replaced, then that will go into the future. So it will add to your cost in the future years up to year T, and then your discounting will be more for those years. Then also you have to calculate the present value of your revenue. So R stands for the revenue here. Now, normally, as I said, R0 could be 0. So depending on the time to build the project, in the early years, you might not have a revenue, as I will show you in a diagram. But you might have a 6-month build time, and then you have also in the same year, you also have some revenue. And then from the next year, you have more revenues until the lifetime of the project, which is the capital T, and you have to discount them as well using the discount factor. And in the NPV approach, you actually take the difference between the present value of the revenues and the expenditure. Basically, you have actually discounted the net benefit over time in NPV. You would expect your net benefit present value to be positive for the project to go ahead. So if NPV that you have calculated is positive, you can say actually you can invest in the fever technology that we have. If it is 0, the investment is sort of, you will not gain, you will not lose, so it's a sort of indifference. And then if it is negative, of course, you will not go ahead with the project. And this is something that we have to be careful about it when we are trying to sell the project. Now, what you need in this to calculate these formulas, of course, are the expenditures or the costs. From the engineering side, for instance, whatever the cost of the renewable energy like solar or wind turbine and the batteries that you are trying to put into the model, and any other cost that you can think about, it can go up to the commissioning cost or the scrap value or whatever that you can think about it, can go into the expenditure. And then in terms of the revenues, what it is actually important, because the revenue comes from the price and the quantity of production that we are producing electricity from the fever technology. So in terms of electricity production, I'm sure that the engineering side also, depending on the capacity and so on, they can have some sort of predictions of how much generation can be there. But also assuming that this generation of the electricity is going to be sold in the market. So there is actually the exact demand for the supply that fever technology is giving. Because if you cannot sell what you are producing, your revenue would be less than what you originally would have thought that you can sell all of your production. Now let's assume that happens because demand is normally on the high side. Let's say we are putting the technology in the area that demand is already on the high side, given that technology. But also you need to have the price, because the revenue comes with the price and the quantity of production. And this price is something that you probably need to make a different assumptions for it, based on the price that it is available in the market, and make some low-high scenarios for every parameter that it is in the model. But also you might want to use more robust approaches, such as base it on a models in the economics and things like that, to find a reasonable price to put there, for instance, a price that has an equilibrium in the market and so on, like we were discussing with Taro. So make it a bit more complicated, but surely you need to have some assumptions about prices. Normally in the calculations, this discount rate and price and so on, these parameters, they are taken sort of constant over time. But again, if you want to make it more complicated, you might want to think about prices changing over time, for instance, in the future. But normally in the calculations, for instance, discount rate is constant. You can find a discount rate from different reports, such as from previously from base reports, or just from the different companies and so on. So it is something that it has normally a range and it is available. And for the cost, it's probably from the companies that you can get a better cost because it is a particular technology that we are looking at rather than overall average that we are looking. And for the price is just the market indications really. Now, this is the diagram that I said it can take place when you calculate the NPV for the individual year. So for example, this is a project that it has 10 years, the first 10 years, and you see in the early years until around year 4, actually the NPV over time is a negative number. So it is only after year 2 that you see some revenue comes in and NPV starts to lift, and after year 4 the NPV gets positive because maybe revenue was not there until year 2. It was only cost for the project. But what we are calculating by NPV is the overall NPV over the lifetime of the project, which it has to make sense and be positive rather than individual years. Now, here is the numeric example. Firstly, because in case you want to see how the numbers are fit in the formula, you can have a look. But also, I want to show a point from this example. You have two technologies that they are generating electricity. Technology one is a capital-intensive technology, such as fever technology, using renewables because mostly the cost is at the beginning. And then technology 2 is non-capital intensive, such as a gas-fired electricity generation. And as you see in the two tables, the capital cost is the big difference, and then the operation cost, which is much smaller for technology 1, which is renewable. And of course, I have changed the lifetime of the project and the discount rate and the time to build for simplicity. Of course, it has stayed the same. So I am focusing on the cost present value here, so I assumed everything else is sorted out. So the cost present value is calculated for technology 1 and technology 2 with a discount rate of 5%. So as you see, the first year it has the capital cost only, and the years to come operation cost has been discounted. So for instance, for renewable is 10, and putting the 5% in the formula, which is on the top, you can have forgotten to put the final numbers, but you will calculate the PVEs or the present value of the cost. So what I'm trying to show is that if you change the discount rate, so I did it for 5% and we are somewhere here, you can see how the cost present value for these two technologies will change. The line in the solid, the curve in the solid line is the technology which is from fossil fuels, which is less capital intensive. And the one in the dotted line is the more capital intensive or renewable technology that we are using, which is capital intensive. You can see that when we change the discount rate between 5% to 10%, the cost present value of the renewable energy technology, which is capital intensive, is not changing as much. Whereas for the fossil fuel technology, you see that when we increase the discount rate, the cost present value comes down sharply. Of course, the reason is that the capital intensive technologies, they have less cost into the future to be discounted. And so therefore, they are less sensitive to changes in the discount rate, which is in a way is a good news for us because fever technology is more capital intensive. But again, as I mentioned earlier, if you have, for instance, replacement of the batteries or any other cost in the middle until the lifetime of the project, then they will be more sensitive to discounting. But having said that, this doesn't mean that we can get away from calculating something like NPV, because at the end, this is only a good news that maybe choosing different discount rates will not affect the cost part, but at the end, we have to show that the NPV is positive from our technology. Now, internal rate of return is based on the net present value. The difference is that the IRR, or internal rate of return, is a rate that gives you NPV equal to 0. So if you use the same NPV formula and put that equal to 0, but instead of having a discount rate in the market, which was I, just have the X and then calculate the X from here, that will give you IRR. That X is equal to IRR. So it's the rate of return that actually gives you NPV equal to 0. When you calculate the IRR, if it is larger than the discount rate in the market for investment, then you will go ahead with the project. So the comparison here is between IRR and I in the market. And if they are equal, you are in difference, normally you wouldn't go ahead with the project. And if it is less than I, then of course you wouldn't go ahead with the project. Now this IRR has some issues, which I will mention later. But as you see, when you want to calculate this in practice, it is more of a try and error. The calculation is not as easy to get the final IRR out of this formula. Now here I have just brought a very simple example with the simple numbers to show you something. So assume that you have a project that lasts for 3 years. So year 4, basically the project doesn't have any net benefit. And you have the expenditure revenues and the net benefit, which is the difference between R and E. And we are trying different discount rates. Assuming that discount rate is 5%, you have ER, you can put them in the formula for NPV and you get a number for the NPV. And then you try another, this I have just replaced the numbers if you want to look and see how it has been calculated. In option B, we increase the interest rate to 8% and calculate the NPV, and that's equal to 0. So this I here is actually IRR because it gives us NPV equal to 0. And then in option C, we change the discount rate to 10%, and then NPV gets a negative number. Now, like I said, there are some problems. Sometimes when you calculate IRR, not in this case, you can get multiple IRRs. And that makes the decision more difficult. So rather than one IRR, which is 8% here, if you had 2 numbers, then you didn't know how you want to make a decision because you have to compare it with one discount rate in the market. But there are some modifications that I will mention later on to resolve this issue. Again, this is the same example, and I just want to show that in option A, your NPV is a positive number, so therefore you go ahead with the project because that was the NPV criteria. Positive, go ahead with the project. And the IRR in this example was 8%, which is also larger than I in option A, which was 5%. And therefore, based on IRR, you also go ahead with the project. So the result is the same. Now, again, I have to note that IRR, when you calculate it, it is in terms of percentages. So it is comparable with discount rate. But NPV, it has monetary values. So for instance, it is in million pounds and so on. So so that's why you compare it with a 0 actually there. In option B, you have the IRR, which gives you the NPV equal to 0, but assume also the discount rate in the market is the same as IRR, it is 8%. You are in difference between the project because your NPV is 0 and your IRR is equal to discount rate. The rules of the both methodologies are the same, gives you the same result. And also, if your I is equal to 10%, your NPV is negative, and you don't go ahead with the project based on the rule. And also, your IRR, which is 8%, is lower than 10%, which is now the discount rate, and you don't go ahead with the project. The point is that if you are only comparing one project to make a decision, the IRR and NPV will give you the same result. Now, it's the matter of academics normally like NPV. They are in the favor of NPV because it has some advantages to it. But maybe the business that you are trying to sell the technology, they are more familiar with IRR or they prefer IRR. So maybe we can just actually try different methodologies. Even we know that they, in theory, they should give the same result for the one project. But in terms of how you want to sell the technology, maybe the language using one methodology works better than the other. But the problem is when you want to compare 2 different projects. Say you have the blue and purple project A and B, and then you want to use the NPV approach to make the decision between 2 projects. If you have 2 projects, so like I said, if you have a fever technology with different types of cost, different types of batteries, different types of renewable energy, option 1, and as opposed to project B, which has different combination, of course, your cost and your capacity for generation and so on can change. So you have 2 different options projects. When you use NPV to compare them, you will go ahead with a project that it has higher NPV. But if you want to use IRR between two projects, you go with a project that has higher IRR. Okay? Now, in this example, if your interest rate is somewhere around below 14%, which is on the right side, on the left side that I am showing now, the project B always has a higher NPV than project A, which means that you prefer project B based on NPV approach. Now, if the interest rate in the market is somewhere above 14% on the right side that I'm showing now, then of course until the NPV gets zero, because if it goes to negative for you are not going to use it, you choose project A. Because A now has a higher NPV. For instance, if you say that your discount rate is about 16%, which I am showing, then of course project A is preferable. But if your discount rate is 5%, then the purple one project B is preferable. If you use IRR approach, IRR is the interest rate that gives you NPV equal to 0, which for project B is around 20%. Sorry, for project A is 20%, and for project B is around 18%. So you go with a project that it has a higher IRR. In this case, it is project A, always. So it doesn't matter where your actual interest rate, discount rate in the market is, whether it is 10% or whether it is, for instance, 15%. You always go with IRR that it is higher. And in these cases, again, NPV is preferable. So that is also another fault that maybe IRR has. Now, maybe this doesn't happen, but maybe it happens that they have contradictory results. Because of these reasons and some underlying theories that also are there and assumptions behind IRR and MIRR, which I'm not going to mention here, of course, but MIRR, which is a modified internal rate of return, was introduced, which resolved some of the problems that IRR had, such as giving you a multiple rates. That was a problem for decision making for one project, and comparing two projects together that you didn't know actually whether you should go with NPV, you get a different result. Now this should resolve the problem. In the calculation of MIRR, we are looking at the future values first. So that's why in the very first slides that I started, I talked about the future value. Here is where we're using it. So whatever value, monetary value that you have from year, whenever you start having your revenue, for instance, let's stick to the example of the base year, you have the cost, which is E0, as I'm showing now. So that is the capital cost in the first year. And from year one, you start having revenue and of course your operation maintenance cost, so you have a net benefit until year T, capital T, which is the lifetime of the project. You all change the values to the final year of the project, which is the capital T. So for instance, for year one, that's N1 is your net benefit in year one, rather than dividing by 1 plus I, you just multiply it by close brackets 1 plus I, then power T minus 1, which this T here is the lifetime of the project, not the same year that we are, which is year one. So for instance, if the lifetime of the project overall is 20 years, year 20, then T here is 20 minus 1, which is 19. So we are going from back forwards rather than backwards. So it's different. Again, in year 2 is T minus 2. And of course, when you get to final year, which is in the future, and T is the same. It doesn't need any discounting because you're actually converting all of the present values of the net benefits, the values of the net benefits to the year T, capital T. Once you calculate this formula, which is Vn, the future value of the net benefits, you now change it to the present value. So Vn is all happening in year T. The monetary values in year T, they have that value. You just discount it once. So over 1 plus R and the power T. T is your, again, lifetime of the project final year. And this R here that you are trying to calculate now is your MIRR. So to calculate, I just summarize this, to calculate MIRR, you equal the cost in base year. Of course, depends on how the flow of the revenues and cost goes, but for simplicity, I am assuming this. The capital cost happening in the first year. So that's equal to the present value of the future values of the net benefit. And this R is something that you have to calculate. That is your modified internal rate of return, which this equality happens there. If MIRR is not larger than the discount rate in the market, then the project will go ahead. So the rule is similar to IRR, but instead of only using the present values, you are using a combination of future values and then converting to the present value. And when you do this, some of the problems that IRR has will be resolved. So this is the same simple example that I brought there. And I have just calculated the future value of the net benefits here. So put the numbers here just in case someone wants to try how to do it. So for instance, for simplicity, the final year is year 3. So you don't have to discount this because you are changing all of the net benefits to year 3 value, which is the future. So that's why the 35 is the same. But for instance, for year 1, you have the 40 here as the net benefit, and you have to take it into the future, 2 years remaining to the future, which is year 3. So that's why it takes power 2 and so on. And once you calculate this, then you divide it by 1 plus R, which R is the MIRR that you are trying to find, and T is the final year of the project, which is 3 years here. You don't count for the base year. And then 100 is here the capital cost, which is happening in the year base year. And then I have calculated the MIRR, which is now 0.066%. Now assume that, for instance, the I discount rate in the market is 5%. The NPV is positive and the project goes ahead, something that we concluded before. The IRR is equal to 8% and the project goes ahead because it is larger than the discount rate. And the MIRR, which I have just calculated, is also 6%, which is larger than I in the market, which is 5%, and therefore the project goes ahead. So as you see, MIRR and IRR are different. And now in this example, this was just a simple example, so they are not that different. And the result is in a way that with all of the 3, you are getting the same conclusion that the project will go ahead, especially between IRR and MIRR. But in practice, the difference can be quite big as well, which will affect your decision making. Right, now the real option. Real option approach, or also called the fair option, is used when you have some sort of uncertainty, for instance, for a policy in the future. Now, maybe it's not directly related to calculating the benefits and so on for technology that we have now for fever. But for instance, assume that we don't have a policy now like this, but assume that the policy can come that supports off-grid electricity generation. But we don't know whether that is going to happen or not, but there is some discussion in the government that maybe some support is going to be there. Now, there is where this approach can be useful, and we need to calculate the real option or the value of the weighting for the policy for our technology. But remember, as soon as this policy is announced, or as soon as the information is about this policy is out there, the real option will drop to 0. But I will show this to you with an example. So again, we are talking about fever project here. Like I said, say for instance, the government is talking in next year, maybe we are going to have a policy that gives some subsidy for off-grid electricity generation per kilowatt hours of generation, for instance. So option 1 is no support policy, which, as you see, that it has a less net benefit for fever technology. And if you have a policy which comes for the government next year, you of course will have a bigger net benefit because you are getting some subsidy, or you are getting some more income in a way because of your generation. Say, for instance, something like the feed-in tariff comes for off-grid. The rest of the variables and the parameters are, of course, the same: lifetime and discount rate. The difference is you see a probability factor here, which for simplicity now I have assumed there is 50% chance that the policy is there, going to be there, approved, and 50% not being approved, but it doesn't have to be 50-50 necessarily. And now, how the investor goes about this? Should they actually start investing in our technology from now, or should they wait until the government actually announces next year that what's going to happen with the policy? So whether they wait or they don't wait to make a decision, that's the question. So again, it is based on the NPV approach. So the underlying methodology is not anything new. Till now, they have all been based on NPV, just there are some variations of how to use it and how to conclude on it. Because there is a probability here, then you can actually calculate the expected net benefit using the formula just on the bottom of this slide. So P's are the probability of having and not having the policy, which are each 50%. And the 500 here is the net benefit if you have the policy, and 100 if you don't have the policy. And it will give you the expected value of 300 for the net benefit. So I have used the 300 here in calculating the NPV on the top here, the first line of the calculation. And 10% is already given. The lifetime of the project is 20, so we discount for 20 years. And it's 1 year to build the project, so we only have costs for base year, which is minus 2,000 here. The NPV is a positive number, it's 554. So till now is a positive number if you take the expected value. Now, whether I have to just start investing in the project or whether I have to wait for next year, then you have to calculate the NPV with the support policy waiting for 1 year. So you know that there is only a 50% probability of this policy happening. So you have to multiply your whole NPV in 50%. And to calculate the NPV, and this is a tiny bit to note that because you are deciding in the second calculation, you are assuming that you are waiting for 1 year. So your capital cost needs to be discounted because it is not happening in year 1 rather than in base year, which is 0. So the top formula is you are investing now. And the second one is you're actually waiting for another year. So the minus 2,000, which is capital cost, also needs to be discounted by the discount factor. And then from year 2 is your net benefit, which is 500 now, because now assuming the policy is happening. And then you start discounting until year 21 rather than year 20, because you have lost your base year without any investment. And that will give you a higher value. Then you take the difference between the second and the first calculation, and that will give you a positive number here, which actually is the real option value or the value of the weighting. If this calculated number is a positive number, then you prefer to wait a year until the decision about the policy is actually made in that year. But as soon as this information is reached to you, this value will drop to 0. There is no value for waiting, of course. So in other words, the investor is happy to pay, in this example, 472, say K or whatever, or million or whatever it is, to get the information about the policy. So if someone can provide them the information, they are happy to pay this amount to get the information, and therefore the value of waiting drops to 0. Now, maybe this is not now something that it is happening for feasible technology because there is no policy to support off-grid as far as I know, but maybe it is also something that when we are researching the project, we can consider that whether we need government to have some subsidy or support these type of technologies, and if we need, like, what is the range of that support that it needs to be, and how it helps more uptake of this technology. Then this approach, levelized cost of energy, which is the final approach that I'm talking about, LCOE, is very popular, but it is only in energy. So in standard economics, you wouldn't see this approach. I have only seen it in the energy literature, really. So what this LCOE tries to do is to calculate the unit cost of generation. That is what it's trying to, unit cost of electricity production. And therefore, it has different components of the cost, including capital cost, operation and maintenance cost, and fuel cost, which for renewable energy is zero. So we don't get rid of the fuel cost in our case, for the fever technology. And in a way, discounts them to find the value for the unit cost of generation, which again, in a way, shows you the minimum value that you have to get actually for this project to be beneficial to you. So the formula that I have used here is based on the Normal formula. It actually discounts the capital cost first by different types of discount rates. So each of these parameters and longer formula at the bottom that you see, they are different. For instance, R here, there are different type of discounting that maybe in different formulas, they can be different as well. So this is something to note. You might see different variations in calculations. So CP here stands for the capital cost that you have already. H is the number of hours a year, which is normally a fixed number, as you see. R is the capital recovery factor, which shows that actually the share of the plant cost that income has to cover over a year for it to be beneficial. So that's why you try to spread it by recovery factor. And then you have the capacity factor, which is basically the share of the generation to the capacity that you have. It is in percentages. You're familiar with this. So this R, which is the recovery factor, in itself used as a discount rate in the market that we have already talked about it. And then it is multiplied there for the capital cost. Then the second component is the operation O&M costs, which is CO. Again, H and F, you are familiar with them now, but it has a levelization factor in this formula, L. And this levelization factor is integrating the increase in the O&M costs over plant. As you know, the O&M costs will increase over time, but this effect goes through L and through the formula, because L itself is depending on I, which is the discount rate, and E, which is the escalation rate. And it is this escalation rate that actually measures the growth in the O&M costs as the plant ages annually. And then through L goes into the whole formula. So like I said, again, this whole L is a type of discounting in finance, which is used here in the Normal formula. It is quite long, but it is possible to calculate it, of course. The fuel cost, it doesn't matter here in our case. It is equal to 0 for the renewable technology, but again, it has a formula, if you like, as well for the fossil fuels. When you add up the different components, capital cost O&M and the fuel is 0, that will give you the LCOE, which is the unit cost of the electricity production over the lifetime of the project. Now you compare this with the price of the electricity in the market, PE. So if the PE, the price in the market, is larger than your LCOE, then the project goes ahead, because of course there is a marginal benefit per unit of generation here, because your P minus C is a positive number. And if your LCOE is actually larger than P in the market, then you wouldn't go ahead with the project because you're going to have a loss. The important point here is that when you're taking a PE to measure, you need to make sure that you are selling your electricity in the retail market or in a wholesale market. Now, normally in the literature is the wholesale market because you are talking about that large-scale generation and the grid and so on. But I guess because we are off-grid technology and we are on a smaller scale, that we are trying to sell the electricity directly to the consumers. So either the ones that you are using the EV charging stations or the one that you are the extra electricity that is going to be sent to the local businesses or the residential area that we were talking about it. So probably is the retail price that we have to look here for the comparison, and that's important because the wholesale price and retail price can be very different. Again, here is an example, numeric example, that I have put different assumptions for the different parameters and the variables. And again, I don't think I need to go through it one by one, but in case you want to do some calculation to see whether you are getting it right or not, these are the formulas, because R needs to be calculated, I, the discount rate, is given, and the lifetime of the project is given, so R is possible to calculate. And then you have to have some assumptions about the escalation rate here as well, so that you can calculate this formula together with the lifetime of the project. And once I have put these here, I will get a number of around 7 pence per kilowatt hours for the electricity that is going to be generated from this technology. Now, if I assume that the price in the market, or it has been already, the price in the market is 9 pence, because the 9 pence is larger than 7 pence, then I will go ahead with the project, because I have a net benefit or marginal benefit for each unit of generation. So again, there are some assumptions here that needs to be made, but it is possible to find them again from some reports and so on. Even some of the companies, they have some assumptions there, or maybe the ones that you are buying a solar panel from them and so on. But again, price is something that you have to check what sort of retail price is an average that you want to consider, especially that the sale of fever technology is limited, maybe to the you have to look into the consumer base as well here, and the demand and supply thing again maybe. Now, the version that I showed to you was based on Nobel, but you will probably see also the more easier versions for the LCOE, for instance, based on Darling and Mundana. They use this formula to calculate the LCOE. So each of them, they have some parameters and don't have some parameters. So in here, the LCOE is basically the capital cost, which there is no discount. It is something like the net present value that I presented, so it's much easier to calculate. CO is the operation cost that they have, just they have used the standard discount rate to discount it over the lifetime of the project. LP here, which you didn't see before, is the loan payment. So if the investor is having some loan that it is paying over the lifetime of the project, of course, that is a cost. So it will add to the cost. So that's why they have discounted this as well, like a normal cost, like CO, like anything else, which was not there before in the Nobel formula. And SV is the scrap value at the end of the project that, again, they have just discounted it as normal. Now, if the scrap value at the end of the project is actually a negative number, that is a decommissioning cost. But the point is to also, there are things like the scrap value or the decommissioning cost and the loan cost that they can be also incorporated into the calculation, which they were not there before. Instead, for instance, something like escalation rate is not here. I think there is something else that is not here as well. The operation and maintenance cost, aging is not here. Levelization cost is not here as well. But instead they have D, which is the degradation rate, which you can maybe get from the producer, for instance, of the solar thermal or the wind turbine or something for that renewable technology. It was not considered before. I haven't tried this, whether it is a possibility. I mean, this formula is, of course, very easy because the discount rates are just the standard discount rates. But whether both formulas, in a way, they can be integrated to capture all of the parameters, I haven't tried this, but maybe that is a possibility as well, so that they can be looked at rather than ignoring them. So in this paper is a paper that it is just published with my colleagues, and we calculated the LCOE for solar energy in the UK, and we used both of the formulas, the Nobel one and the one which appeared to be simpler, to see whether they are different or not. The end result was very similar. So both in terms of the values that we got, the second formula had lower values in terms of the number, But in terms of the trends for the graph that I'm going to show you here, they were very actually close. That's one point. The second thing that maybe again is useful for the project is that we decided to break down the systems to small and large and so on based on their capacity value. As you see on the top graphs, the system capacity is smaller, very small on the top and left, is up to 4 kilowatt, and the second one top right, it is between 4 and 999. Again, it is on the small side, and the bottom you have 10 and 49.99, so it gets larger, and then you have large scale, which is above 49.99. Firstly, you will see that this is over years we have calculated is LCOE, and the thick line in the middle is the medium value, and then we have high and low scenarios, the dotted lines on the top and bottom, which shows the range. So the trend is showing, for instance, for solar energy, the LCOE is going down over time. So it will be more beneficial for the investor to invest in it and produce electricity from solar energy. Possibly something like this has been done or can be done for wind energy as well, to prove that actually which one is going a sharper increase in LCOE over time. But what I wanted to say here is that when you have a small scale solar energy, you have a higher LCOE, much higher LCOE. So for instance, if you look at a year 2021 and very small system, you see that it is 145 in terms of pound per megawatt hours. It is sort of similar number when you get a little bit larger in scale, but when you get to very large scale, for instance, between 10 and 49.99, it drops to 96 for year 2021, and then even larger than that drops to 51. So the larger the scale, the LCOE would be lower, of course, because of the economies of scale of the generation. But probably our technology is not going to be large scale as much, but that is the engineering part, of course, that where it falls and how much it can change. But it will give you an indication of maybe if you have a larger as opposed to smaller capacity, then maybe the LCOE would be smaller because of the economies of scale, and maybe it makes the project more beneficial in the longer term. Right, I think that was my last slide, and some references here.